Hi, in this video we're going to take a look at applications of maximum and minimum. Now, to explain what we mean, imagine we've been given a piece of sheet metal, so it's a fixed size, and we've been asked to make a cone, as you can see there on the screen, such that the cone has maximum volume. So which is the best shape? Is something which the height and diameter are roughly the same, or is a tall but skinny one give you the maximum volume, or does one that's fairly short height but fat base? Which of those gives us the maximum volume? So we're going to have a look at ways that we can determine this. Now let's take a look at an example. Let's say that a farmer wants to fence a paddock along the river. So he only has to fence three sides, the river being the fourth side. And he has 50 metres of fencing wire and wishes to make the paddock such that it has a maximum area. Just fixing up the spelling there. So what will the dimensions of the paddock look like? So let's say the blue represents their river, and we're going to map out our paddock as such. So if we make the width x metres, that means then that the length then is going to be 50 minus 2x, because the x plus x and the length have to add up to be 50 metres. So that means then the area of our paddock is going to be equal to the length, which is 50 minus 2x, times the width x. I'll simply put the x term first. So what we want to decide now is which value of x is going to give us the maximum area. Now, before calculus, one way we would have done this is to turn to a spreadsheet. So in a spreadsheet, we might have labelled one column x, the other column the length 50 minus 2x, and then the area then is the product of these two values. So if we start with 0, and of course 0 is a useless value, because that simply means that you have a length of 50 metres and no width, so it's just a line. So therefore we've got 0. Now if we go to 1 metre, that means now the length is 48, so we've got 48. So by putting a formula in here, we were able to then generate values within the spreadsheet. So as you can see, when x is 6, it's 228, it's still going up. 11, it's 308, 12, it's 312, 13, it's 312. So that means that the maximum area is somewhere between these two values. And if we keep going, make the width 14, we see now that we're dropping off. So when we get back to 25, the width of 25, that would mean two widths of 25, means there's no length. The length here would be 0. And if we went to 26, we see now that we've got negative area, which is impossible when we're talking about a real situation. Now we know that back here, the maximum area occurs somewhere between 12 and 13. So what we could do then is drill down and sort of take increments, say, of 0.1 between 12 and 13. So what I've done then is I've gone up in increments of 0.1 of a metre, and we see that when we get to 12.5, we get a maximum of 312.5, then it starts to drop off again. So from here we can see that the dimensions of the paddock are going to be that if the width is 12.5 metres, the length, which will be 50 minus 2x, will be 50 minus 25, means that the length is 25 metres. So that's one way of determining the dimensions of the paddock for maximum area using a spreadsheet. However, let's now take a look at an approach using calculus. So here we come back to our area, and we've got the formula there is A equal to x times 50 minus. Now this equation suggests that the graph is going to be a parabola, because if you expand it, you'll have 50x minus 2x squared. So the highest power is x squared, means it's a parabola, and because the x squared term's negative, it means it's going to be an upside down parabola. So therefore, it will have a maximum, and the maximum is where its vertex occurs. So we can use the derivative to find where the gradient is 0, and hence find the x value for which that occurs. So if we look at the, here's our area there expanded. So if I just keep that, so taking the derivative gives us 50 minus 4x. Put that equal to 0, and that tells us that the turning point or the stationary point is going to occur at 12.5. Now, we can use a sign diagram, or we can graph this to confirm it. So if I just look over here at our graph now, like we said, it's an inverted parabola, and the turning point here, the stationary point, is occurring when x is equal to 12.5. Here it is down here. You can see the scale is 5, 10, 15, 20, 25. So by symmetry, it's at 12.5, and when you substitute 12.5 back into the equation, that's going to give us 312. Just fixing it up, it actually was 312.5. So we can see from calculus, a turning point is 12.5. The dotted red line shows that a tangent drawn at that point is horizontal, has a 0 gradient. And we know that the y-ordinate there is 312.5. So the maximum area of 312.5, fix that up as well, it's achieved when the width is 12.5 meters and the length is 25 meters. If you look at the equation of the graph, it tells us that we could have worked this out again without using calculus, because we can see that factored it's 2x times 25 minus x. So when you find the horizontal intercept when a is 0, that would give you 0, which is this point here, x equal to 25 over there. And because of the symmetrical nature of a parabola, we know that its turning point, or its vertex, occurs halfway between here and here. Notice that the graph here, when it goes below for x less than 0, it's irrelevant here, because we have no concept of negative length, so therefore it's not realistic to talk about negative areas. So the domain of this problem is really between 0 and 25.